Good morning everyone. Today we are going to solve problem 2.53 on lesson 12, temperature effects on axially loaded member, from the book Mechanics of Materials, 4th edition by Ed Ferdinand P. Beer and Company.
So, our objective for this problem is calculate the effects, stress and reaction of temperature change in axially loaded members. So first, we need to draw the free body diagram. We need to compute cross-section area of portion AB and BC respectively. So first, we solve for area. AB is equal to pi over 4 times 60 to the power of 2 times 10 to the power of negative 6 meters squared. So for AB, we have 2.86 times 10 to the power of negative 3 meters squared. So we have portion BC is equal to pi over 4 times 40 squared times 10 to the power of negative 6 meters squared. And we have 1.253 times 10 to the power of negative 3 meters squared. Since the portion AB and BC are homogeneous and of uniform cross-section, the strain developed due to temperature rise is E sub T is equal to delta sub T over L, and both A and C points are fixed. Therefore, a compressive force will be induced in the rod as shown. So in order to solve this, we have a given for AB, length is equal to 1.1 meters and alpha sub S is equal to 20.9 times 10 to the power of 6 over degrees Celsius, and temperature is equal to 42 degrees Celsius. And for BC, we have length 1.3 meters, alpha sub S is equal to 23.9 times 10 to the power of negative 6 over degrees Celsius times, and temperature is equal to 42 degrees Celsius. So we have formula for stress total is equal to stress AB plus stress BC, or sigma T is equal to sigma AB plus sigma BC. So we have stress total is equal to length sub AB times alpha S times delta T plus LBC alpha B times delta T. And we will input that in our calculator. We will have 2.27052 times 10 to the power of negative 3 meters. And due to induced compressive force, the deformation is shortening of rod ABC. So we have delta P is equal to pressure times length sub AB all over elasticity AB times area AB plus pressure times length BC all over elasticity BC times area AB. And again, let's input it in our calculators. We have delta P is equal to 18.082 times 10 to the power of negative 9P. And under imposed constraints, delta P is equal to delta T. So in other words, 18.082 times 10 to the power of negative 9P is equal to 2.27052 times 10 to the power of negative 3, or P is equal to 125.568 times 10 to the power of 3 newtons. A compressive force P is developed due to the temperature rise. Therefore, the normal stress in portions A, B, and BC are respectively sigma sub AB is equal to negative P over A sub AB. And we will input that in our calculators. We will get negative 44.433 MPa. And in portions BC, sigma BC is equal to negative P over ABC. And again, we will input that in our calculators, and we will get negative 99.974 MPa or negative 100 MPa. And for question number 2 or letter B, due to induced compressive force, the point B will be more upward and equal to deformation of portion AB under load, and due to temperature rise B will be more downward and is equal to deformation of position AB. Delta B is equal to delta AB sub B minus delta AB sub T. So delta sub B is equal to pressure times length AB over elasticity B times A sub AB minus length of AB times alpha B times delta T. And again, we will input that in our calculators, and we will get negative 500.09 times 10 to the power of negative 6 meters, or we have delta sub B is equal to negative 500.09 times 10 to the power of negative 6 meters, or negative 0.50,009 millimeters.
That is all for today. Thank you and God bless.